Let's look at conditional probability problems with cards. Cards and dice and flipping coins are good because they're very well defined, and we don't have to have a table of data. But they are sometimes a little bit removed from the real world. But they're great things to think about. So the first problem, these are both from Bach, Vellman, and DeVoe, chapter 15. You draw a card at random from a standard deck of 52 cards. No tricks here. Find the following conditional probabilities. Okay, so this is pretty much a warm-up on conditional probabilities, but it'll tell us a little bit about how they work. First is the card is a heart given that it is red. Okay, let's look at that. Well, so the simplest way to do this is if we can figure out the appropriate sample space, all the different outcomes, given the information that we're given, and then look at the outcomes that we're interested in. Okay, so it's not going to be divided by 52 possibilities. The denominator is going to be all the red cards. Well, how many red cards are there? There's 13 hearts and there's 13 diamonds. So there's going to be 26 total hearts and diamonds. And then the card is a heart. Well, how many hearts are there? There's 13. 13. Okay. So that's just going to be 1/2. Okay. Or 50% probability. Okay. Now, let's compare that. Suppose we just looked at the absolute probability, the unconditional probability. Simply that the card is a heart. Okay. So we compare, they're not asking this, but I want to illustrate this. Compare to the unconditional, or I would sometimes call it the absolute probability, that the card is a heart. Okay, so somebody's drawn the card and they just give it to you. What's the probability that's a heart? In this one, it's they've drawn the card and they sneak a peek at it and they say it's red. What do you think the likelihood is that it's a heart? Well, it's going to be 1/2. It's just 13 out of the 26. Okay, the unconditional probability. Let me write this down. This is P of heart given red. Okay, versus just the unconditional probability P of a heart. Heart. Okay, and that's going to be excuse me, the same 13 outcomes. We need an equal sign. The same 13 outcomes out of all the possibilities, and that's 1/4. Okay, so I might as well ask, that's 25%, of course. Might as well ask the big question here, which is, are these independent? Are being a heart and being red independent? Absolutely not, because being red makes it a lot more likely the card is a heart. Okay. And it's exactly the difference between those, the absolute unconditional probability and the conditional probability, that tells us that very numerically. Okay, now what about the card is red given that it is a heart? That's interesting. Okay. Well, let's see. What would the absolute probability of card is red be? That would be 1/2. Okay, because half the deck is red cards. All right, but we know it's a heart. Okay, so let's see. Probability of red given that it's a heart. Well, we could do it in the kind of just look at the sample space and outcomes way. Okay, given that it's a heart, there's 13 hearts, and of those 13 hearts, how many are red? Well, every single one of them. So that must mean there's sort of an easier way to think about this. Okay, if you know it's a heart, you're absolutely certain it's red, because heart is a subset. It's a special case of the event red. Okay, so this is a very special case of conditional probabilities. If the event that you know is true is actually a subset of the event that you're interested in, you're always going to get 100% for the conditional probability. Okay, so certainly, given that if you compare all these three, given a random card, knowing that it's a heart, not knowing it's a heart, the probability that it'll be a heart is 25%. Knowing that it's red definitely increases the probability that it's a heart. But if you switch it around, the probability that it was red to begin with is 1/2. If you know that it's a heart, that doubles it again to a full 100%. Okay, so all these numbers are going to be different. Okay, now let's look at this one. This is rather different. Probability that it's an ace given that it's red. Okay, let's think about this just from first principles. Let's not worry about counting outcomes just right now. If I'm dealing you a card and you really, really want to get an ace, you're going to win the game if you get an ace, and they sneak a peek at it first and they say, ooh, it's red. Does this make you happy? Does this make you sad? Does it make you feel like it's more or less likely to be an ace? I would hope it doesn't, because I claim these events are going to be independent. Okay, so let's check that. Let's just look at the outcomes. Okay, given that it's red, there's 26. Now, how many red aces are there? There's the ace of diamonds and the ace of hearts. That's 2 out of 26, or 1 out of 13. Okay, or that's the same as 4 out of 52. And guess what 4 out of 52 was? That's just the probability that you get an ace without saying anything. Okay. These guys are equal, and that's indicating that ace and red are independent events. Okay. That's really, really important. So these are example of independent, whereas these guys are not independent. Okay. Now what about D? Given that it's a face card, what's the probability that the card is a queen? Okay, so queen, given that it's a face card. Okay, well, let's see. How many face cards are there? There's Jack, Queen, King, and there's 4 suits. There's going to be 12 of those guys, and there's 4 queens, queen of all suits, and that's going to be 1/3. What about that? Compare that to the probability that you just get a queen, for example. Well, that's definitely not just the probability you get a queen, because that would be just 1 out of 13, because there's only 4 queens out of the whole 52 cards. And so again, these are definitely not independent. Hopefully that shouldn't surprise you. If I tell you that the card is a face card, you're going to be thinking, hey, now it's not a super bad probability that it's going to be a queen. Suppose I want to get a queen to win the game. Then I'd like to hear this information. So notice how I keep phrasing this. It's a good way to think about it. I'm interested in a certain event happening, like it being a queen. They give me some other information, and I'm trying to decide, do I like that? Does that make me happy or sad? And if it does, then they're not independent. That's assuming I have a pretty good intuition about the probabilities, which we don't always. Okay. So that's some simple ones with conditional probabilities and independence with cards. Now here's another card problem. It's going to be a little more involved. You're dealt a hand of 3 cards one at a time. Find the probability of each of the following. Okay. Now, very important, this is with no replacement. Okay. They don't deal you a card, then just tell you to look at it, memorize it, put it back in the deck, and then shuffle it, and then give you another card. Okay. So this is really a great example of drawing without replacement. Okay. What's the first case here? The first heart you get is the 3rd card dealt. See, you actually have to read that a couple times so you can see what it means. Okay, it means you don't get a heart on the first 2 deals, and then you do. Okay, so as with lots of probability problems, the key is to say it in terms of ands. Okay, the probability that we're looking for is that the first card is not red. Not a heart, sorry. Okay. And the second card is not. Shoot. Oh, shoot. Silly of me. Put that back. Okay. Not a heart. And the third card is a heart. Okay, so we've got and, so we'd be tempted to use the simple multiplication rule from chapter 14, but we cannot do that. That's really important, because whether or not the first card is a heart affects the probability of the second card being a heart and the third card being a heart. If the first card is not a heart, there's still just as many hearts in the deck and fewer total cards. So we're going to increase slightly the probability that the second card is a heart. If the first card was a heart, we would decrease slightly that the second card is a heart, etc. Okay, so we can't use the simple multiplication rule, but we can use the general multiplication rule. We can say this is the probability that the first card is not a heart times the probability that the second card is not a heart, given, let me put little spaces in there, that the first card is not a heart. And then times the probability that the third card is a heart, given this guy. Okay, wow, that seems kind of intricate, doesn't it? Okay, but it's really a good way to think about it, and it's really not as hard as it looks. Okay, and in fact, we can just illustrate this with with a diagram. Okay, so we're going to get we're looking at all cards. Okay, and then we're going to go to the situation where the first card is not a heart. Whoa, that's not what I wanted to do. Okay. All right, so that's the first stage of this. Well, the first card is not a heart. That's going to be all the other 3 suits. That's 3 suits out of 4. And so that's going to be a 3/4 probability. Okay. Now, we're going to go from the situation we now know the first is not a heart. And we're going to combine that. We're going to go to, what about the situation where the second card is not a heart as well? Ooh, I don't really need to do that. Okay. Okay, so that's this guy. So we know that we've got a 3/4 probability for the first card not to be a heart. Given that, we want to find out what's the probability that the second card is not a heart as well. Now this is where it gets a little tricky. One of the cards has already been dealt. This was really a 39 out of 52. I probably should have done it that way. Okay. 39 non-heart cards out of 52 total. Now there's only 51 cards left. Okay. How many non-hearts are there? Well, I've pulled one of the non-hearts, one of the 39 out of there. So it's going to be 38 out of 51 non-hearts. Okay. So this is probably the trickiest stage of it, is to realize that since we pulled one of the cards and it was known not to be a heart, this is the given that the first card is not a heart, what's the probability the second card is not a heart? Our new sample space is basically 51 possibilities, equally likely possibilities, and we're interested in the 38 non-hearts out of that because we did pull one of the non-hearts out. Okay? Now, what's the last one? Okay? Now we've got the going from the first and second not being heart, and we want to go to the third is a heart. That's this conditional probability. We're now further along these stages, let's say, and we know that the first card is not a heart and the second card is not a heart. So we've got 50 cards left on the bottom, and we now want to know how many hearts are left. Well, these were both non-hearts, and so we've got 13 hearts still left in the deck. So the probability at this stage is 13 out of 50. Okay, so we're really going down, we're going down a line. Let me put these all in a chain here. The reason I'm putting these arrows is we're going to build eventually what's called a tree diagram to look at all the different possibilities. Oops. There we go. And we're going to build a tree. This is a simple example of what's called a tree diagram. And at each stage, we have a probability, and when you chain things together, you multiply. And it's an illustration, it's a way to organize the general probability, the general multiplication rule. We're taking the 39 out of 52 that we got originally. Then we're multiplying it by the conditional probability that the second card is not a heart as well. And then we even multiply it by another conditional probability of getting the 13, one of the 13 hearts out of the 50 remaining. And that turns out to be 247 over 1700 and 14.5%. Okay. So that's a bit of an involved calculation, but it's a prototype for a lot of the calculations that we do, and in fact what's called these tree diagrams. Okay. So it's not the only way of doing this problem, I have to say. There's other ways of doing this with like things like combinations, permutations, but it's a way that fits in with the general multiplication rule. Okay. What about your cards are all red? Diamonds or hearts? Okay. So let's look at that as well. Probability of all red. Okay, it's going to be the probability that the first is red times the probability that the second is red given that the first, I keep doing that. Spaces work weirdly in math mode, that's why this is hard for me. Okay, times the probability that the third is red given that the first and the second are red. Okay. So it's a chain, and each thing in the chain we add more and more conditions. We know more stuff. We know nothing here. It's just what's the probability the first is red. Now we know the first is red. What's the probability of the second condition coming in? Now we know the first two conditions. What's the probability of the third condition coming in? And we just multiply them in a chain. And I'll do it a little quicker without the kind of chain of arrows here. Okay, the probability that the first is red is just 26 over 52, or 1/2. Okay, the probability, given that the first card was a red card, okay, now there's 51 total cards, and there's only 25 red cards left. Oops. Now, the third one, we've pulled 2 cards out of the deck. They were both red. What's the probability that the third is red? Well, there's only 24 red cards left out of the 50 total. Okay. So each of these conditional probabilities are not that hard to calculate independently of each other. Okay. Given that I've taken a deck of cards and I've pulled 2 cards out and I know they were red, what's the probability of giving a red card out of that special deck? How many cards are in the deck total? 50. How many red cards are in the deck total? 24, because I know I pulled 2 red cards out. Okay? And then I just multiply these together. 2 out of 17, which is, let's get the number. Okay, about 0.118, or 11.8%, let's say. I usually do it in percent. Okay. So that's a quicker illustration of the same kind of rule. Again, not remotely the only way to do this, but I want to keep illustrating the general multiplication rule. It's a very powerful rule. You get no spades. Okay. No spades. Okay. Well, that's the probability that the first is not a spade times the probability, oops, of the second being not a spade, given that the first was not a spade. And again, the reason we all have to do this very carefully using conditional probabilities is that these are not independent at all. None of these are independent. If I know that the first is not a spade, it does affect what I think the probability is of the second or third getting not spades. Okay, so getting no spades is an and again, and it's the first is not a spade, the second is not a spade, and the third is not a spade. And so I'm using the general multiplication rule again. Given first, second, not spades. Ooh, this doesn't even fit anymore. There we go. Okay. Alrighty. So the first being a non-spade is 39 out of 52. That's the other 3 suits. Okay. So now I've pulled 1 card out. So I've got a new probability problem. Again, the key to conditional probability is just treat each one as a brand new probability problem if you get confused. It's a new deck of cards. It's just a weird deck of cards that's had 1 non-spade pulled out. And so it's got 51 cards, and it's got 38 non-spades because I pulled 1 of the non-spades out. Okay, 13 spades still. And then there's 37 non-spades at the second stage out of 50. Okay, very similar to B. Ooh, you have at least 1 ace. Now that is different. At least 1 ace. Could be 1 ace, or 2 aces, or 3 aces. Now, ors can be dealt with sort of on their own terms, but at least 1 is usually dealt with using the complement property. So at least 1 ace, that's the complement of, whoa, I don't want to print. That was Control P, Shift P. No aces. Okay. So at least 1, it's the case that you get at least 1 ace. If it's not the case, you get no aces at all. And this is going to be easier. It's an and we can use the general multiplication rule. Okay. So no aces is very much like what we just did. It's the first, not an ace, times the, I keep doing that, times the probability that the second is not an ace, given that the first is not an ace, and then times the probability that the third is not an ace, given that the first and second are not aces. And I'll make that more visible. Okay. So it's 1 minus this product. Okay. Probability that the first is not an ace. Oops. 52 cards here, because it's an absolute probability. I haven't taken out and made a new deck with a reduced number of cards yet. Non-aces, that's 48 out of 52. Okay. Times new deck, 51 cards. I know that the first was not an ace, so there's still 4 aces left in there, but I want how many non-aces there are. So that's 47. And then the first, I've got a 50 card deck here. The first and second were not aces, so there's still 4 aces in there, and I still have to avoid those. 46. Now I'm interested in this number. Let's actually evaluate that numerically. Okay, I wasn't sure about that. 21.7%. Okay. So, getting on one card deal, it's just 1 out of 13, much less than this to get an ace. But with 3 cards, the probability you get at least 1 ace is not actually that bad. It's better than 1 out of 5, even though that aces are only 1 out of 13 of the cards. But to get this number exactly, we've got to do something like this that takes into account the fact that I'm drawing without replacement. Okay, so this can look kind of intimidating with all these conditionals and all this kind of stuff, but we'll get a lot of practice with it. We'll do what are called tree diagrams, as I said, and I want to make sure that at least this each individual step is not too implausible. That if I hand you a deck of cards that has had 1 card drawn out of it that wasn't an ace, it's not that complicated to calculate this number. It's got 51 cards total, and it's got 47 non-aces because the 4 aces are still in there. That's where these individual numbers come from. Then the general multiplication rule puts them together, and then sometimes we can use other rules like the complement rule. In this case of at least 1 is always very useful.